Great. So thank you everyone for joining. We're really excited to have another talk in the CLARIPHY series of topical meetings around the intersection of AI and physics. So today we have Gilles Louppe, Liege, talking about the frontier of simulation-based inference. So thank you for being here, and I'll turn it over to you.
Thank you. So first of all, thank you, Savannah, for the invitation. It's a pleasure to see some known names. We don't see each other, but at least I know a few names. So what I've decided to talk about was our work around simulation-based inference and the broader context, which we've described in a review paper that we've called the frontier of simulation-based inference. So I don't know how you usually organize the talks, but as far as I'm concerned, it's fine if you interrupt during the talk and have questions, and I will be glad to answer them. But of course, we can delay that to the end. So first of all, I would like to thank my co-authors, so Karl Kramer and Johan Bremer. So I stole some of their slides for this talk, and we've been talking about this topic now for a few years, and so we built. We had a few presentations, quite a few presentations about that, and what I will present has been adapted and inspired from some of their talks. So thanks to them. All right. So the context is the one of scientific simulator in physical sciences. So if you look at the across the whole spectrum of length scales, so from the study of the fundamental particles in collider experiments up to the study of the universe, in all of these fields, what is common is that theoretical models are now expressed and formulated as computer programs that we call scientific simulators. And these simulators allow researchers to basically express in some kind of forward fashion the phenomenon that they want to study. And so you find that, of course, in the case of physics, in particle physics, but it's also true as you go higher and higher in across the length scale. So in chemistry, in microbiology, in neuroscience, in the study of ecological systems, in weather and climate science, in epidemiology, of course, that we all know about now. You can really study the spread, for example, of diseases using simulators. And then, of course, in astronomy with the study, for example, of gravitational waves, gravitational lensing, cosmology, the study of the universe itself. So even though these simulators are very common, because they really are a natural way to express a mechanistic model, at the same time, unfortunately, they are very poorly suited when it comes to inference. And that will be the topic of today. How do you do inference when the model that you've described is a computer program? So the context, we could abstract the problem in this way. At the middle, we would have a scientific simulator, which is represented by this black box. And this black box gets as input some parameters, like for example, some model parameters, and that I will call theta. And when you set these parameters to your simulator, then you can run it. You can just push a button, and then it will draw random observables. It will produce realizations that we call observables, and that would basically correspond to what you expect to see in reality or in your experiment. And of course, the simulator usually is stochastic, and that stochasticity is modeled through latent variables that I will denote by Z. And so going from the left to the right, so which is what we call prediction, is usually quite easy because it just amounts to run the computer program, and it's expressed in a very natural way. And you can use that to generate samples. And in particular, what the sample that you generate are those that correspond to samples X that you would have drawn from what we call the likelihood function or the conditional distribution of the observable for some parameter values theta. Now, what is difficult, but what is actually the most interesting from a scientific point of view, is to do the opposite. So given some observations X, what we would like to do is to inverse the simulation in order to retrieve the parameters theta that would be compatible with these observations, right? But in this case, it's quite difficult because we don't have a direct access to the likelihood function, right? Because to do that, that means we would have to integrate over all latent realizations of all realizations of the latent variable z's that could have led to these observations, and that would amount to evaluating an integral over all the values of z, and that's just not possible in practice. This is intractable. So maybe to make things a bit more clear, what you have to imagine is that these curves represent random trajectories that you would sample as you run your computer program, right? And when you run your computer program without conditioning anything, this would be the equivalent of just sampling from the joint distribution of the parameters of the latent and of the observations, right? And so when you go from the left to the right, you're doing predictions and you would be sampling these trajectories, and some would be more likely than others, right? And some would be less likely. And this is represented by the shade of the curves. Now, what we want to do is not just sample observations. What we want is to basically clamp some specific observation X, and then to retrieve all the trajectories that are compatible, that would lead to these observations that you have gathered in your experiment, that you've collected in your experiment. And that would be equivalent to the sampling of the conditional of the parameters and the latent given this observation X. And now you can understand why it's difficult, because when you run your simulator forward from the left to the right, you basically don't know in advance where you will end up with, right? But that's exactly what you want to do. You would like to identify all the trajectories such that when you continue and until the end of these trajectories, you end up in this with these X values. So this is why it's difficult. It's a tough problem. All right. So to motivate this framework, I will take the case of particle physics to really highlight where this intractability arises. So in particle physics, what you do, and sorry if I make mistakes, I'm a computer scientist, but I will try to explain what I understand from the bits of physics I've learned during these past years. But so you start with this theoretical model, the standard model of particle physics. And the nice thing about that is that you can basically write this into a computer program and then simulate what would be the effect of the collision of high energy collisions in an accelerator, for example. And so you can simulate, you can write a computer program to simulate the outcome of these collisions according to this standard model of particle physics. And then you can also simulate what you would expect to collect in the instrument. So how the electronics of the instrument would respond to this to the outgoing particles after the collision, right? And so in terms of the framework, what we would have is that we would start with the standard model of particle physics. This guy is parameterized with a few parameters that I now just collect together with this theta. But of course, this theta is made of several individual parameters. Then you can simulate the whole chain from the standard model of particle physics up to the outcome of the detector. And then, of course, you build the actual detector, you build the actual instrument that will make these collisions. And then you collect some data, some observations. And then given this data, what you are after is what you want to do is try to identify the theta value, so the parameters in the standard model, in the Lagrangian, that would be compatible with the observations that you have, right? And this is what you do, for example, when you try to, I think, you want to make measurements on some of these parameters. Right, now the interactability comes from the fact that this simulator that is in the middle is quite complicated and involves a chain of different processes that you simulate one after the other. So you would start with the theoretical parameters, and then after the at the very next instant after the collision, you would have a first description that would involve a first series of latent variables that would correspond, for example, to Parton level momenta. And this, then you would have processes that would basically describe how this fundamental particle would radiate and themselves would produce other outgoing particles, right? And so you would have, for example, another level of latent variables that would describe the showers that would emerge from the collision, and then how the outgoing particles would themselves interact with the electronics, with the instrument that you are considering. So for example, this would be in the case of CMS. And then if you can simulate the electronics, you can also simulate what the software that you would use to ingest this data would itself produce as byproduct, right? And in this case, that would be the final observable that we would consider. And now this is, if that means now if you want to evaluate the likelihood of one particular observable generated by the software that has read the data that was just produced by a collision, that means we would have to evaluate these triple integrals in which we've marginalized out the three levels of latent variables, right? The Parton, the showers, and then the detectors, right? And this is just too complicated. There is no way you would be able to evaluate this integral. All right, but still, so this is an obstacle, but this is something you've been doing actually in physics for quite some time. So how did you do that? How did you solve the inference problem? Well, before I tell you how you did that, but I'm quite sure you know that, but maybe you don't see things in this framework, which is why it can be interesting. I will first define the different problems that you could be considering when it comes to inference. So, but when I say you want to solve an inference problem, that might be basically one of these three different problems, depending on the statistical framework that you are considering. So you would start, as I said, with a simulator, which is some function, some computer program that lets you generate samples. So a certain number n of them that you would decide. And these samples would be drawn from the conditional distribution of the data given some parameterization of the model parameters. For example, you could draw observables x conditionally on the value theta I of the model parameters. And when you do that, of course, you are also free to decide which of the model parameters value you want to set to produce these realizations of the observables. Then you would have also access to the real data that you have collected in your experiment. And in this case, we would make the further assumption that there exists some parameterization of your computer program, which would lead to this specific observation, right? So that there is, in a sense, some kind of true ground truth theta value. And this is, of course, only true if the model is well specified. And then if you're Bayesian, we would also assume that we start with a prior that basically summarize our beliefs about the model parameters. Then, given the setup, the problems that we would like to solve are, for example, to just find good point estimates of the ground truth parameters of theta true. And that would be the case, for example, if you would like to identify the maximum likelihood or to compute maximum likelihood estimates. You could also be interested in trying to construct confidence sets around the true model parameters. And if you're Bayesian, what you would be after is the posterior, which would be the conditional distribution of the parameter given the particular observation that you have collected, right? And you would either be interested in being able to evaluate the posterior density or just to be able to sample from it. Savannah, if you see that I'm taking too long, please do not hesitate to tell me. All right. So to solve these problems, the research community has been quite active, and different algorithms have been proposed over the last decades. I would first put together what I call the traditional methods, which are methods that have been used in a few different fields and that you can use, that have shown some success for simulators which are not too expensive, or when the data dimensionality was not too large. And in these traditional methods, I will put methods that consider traditional density estimators like histograms, which is what has been done traditionally in particle physics, and also approximate Bayesian computation, which is an algorithm that you can use to approximate the posterior in this setup. And then, and this is precisely the topic of today, since the last, I would say, 5 years or so, in parallel to the rise and to the improvements of deep learning, quite a few new methods have been proposed to solve this exact same problem, but reaching higher data dimensionality. So the same methods are able to deal with data that are that can be, for example, images or very large images or large vectors of value. And at the same time, some of them are also able to deal with simulators that are more and more expensive to run. And so if I have time, I will try to go over histograms, and then I will tell you about how we basically can generalize this approach with learning likelihood ratios with neural networks, and then how we can further improve that by going into the simulator code, the computer program, to extract more information, and then to obtain better sample efficiency, which then result in being able to deal with simulators that are more expensive to run. All right, so I will start with the frequentist approach and what has been done traditionally in physics. So usually it starts with the Niemann-Persson lemma, which states that the likelihood ratio, which is the ratio between the likelihoods of the data with respect to some null hypothesis parameterized by theta 0 against an alternative hypothesis parameterized by theta 1, is the most powerful test statistic if you want to discriminate, if you want to decide between one or the other hypothesis, right? And so because of this reason, because it's the most powerful test statistic, this is the test statistic that has been used traditionally in particle physics. But still, we are in a setup where, okay, this seems like a very strong statistic, but it's defined as the ratio of these likelihoods, and I don't have access to the likelihood, right? Because I'm in this intractable scenario where I cannot evaluate P of X given theta, because that would involve integrating over all these random trajectories in my computer program. So how do you solve this problem? How do you go around this problem? Well, the trick is actually quite simple. What you can do is instead of working directly with the observable X, you would work with summary statistics. So you would define a projection of the data that you will define through a function S that would ingest this data and then would produce as output just scalar values, right? And we would call these scalar values summary statistics that I will denote by X prime, right? And then the idea, the trick is quite simple. It would be to say that, okay, I don't have access to the likelihood, but I will postulate a surrogate. I will approximate this likelihood function as the likelihood of my projected data, right? So I will say that my likelihood P of X given theta is, so I will define an approximation of that because of the hat in the notation, and I will define it as the likelihood of the projected data. And this is something you can do easily. In particular, if x prime is now just a scalar made of just a scalar value, you can just approximate this likelihood of the project data, for example, using histograms. And these histograms, you can build them in turn by just running your simulators many, many times, and then filling the bins of these histograms for different values of theta. And then now the assumption that you do is that you will say, okay, then I will say that my likelihood ratio for the original data for some null hypothesis against an alternative is approximately equal to the likelihood ratio of the projected data, right? And then you move on, and you can use this now approximate test statistics to carry on carry out your analysis. And this is precisely what you've done, for example, for the discovery of the Higgs boson. There should be an animation. Let me refresh this. In which you've used this trick to distinguish between background only, which was one hypothesis, against background plus signal, in this case, the signal being the process corresponding to the Higgs boson. But the trick, what made this analysis possible is that you knew you had to project the data across some particular variable. So you knew in advance what was a good projection function S, which in this case was the mass of the 4-lepton system, which I have no idea what that is. But indeed, if you project the data on this variable, you keep enough statistical power in order to be able to distinguish between one or the other hypothesis. Right? Now, the issue is that when you face a new problem, you maybe not know in advance what would be a good function, what would be a good projection function to use, right? And if it's a new problem, maybe you don't have any idea, or it could be that there are actually several good projection functions that you could use, and which one should you use? It's not really clear. So fortunately, you can automate this step using machine learning, and this is called the likelihood ratio trick, and which is basically a trick that you can use to directly learn the likelihood ratio. And the neural network then that you will obtain will be the projection function itself. And so the idea is quite simple. Is to say that, okay, you would be training a classifier, which could be, for example, a neural network, but it could be any other machine learning model if you want something else. And then you train this binary classifier to distinguish between data that would be simulated from the null hypothesis against data that would be simulated from the alternative, right? So the classifier would receive as input some X values, and then would have to say, I think this X value comes either from the null hypothesis or the alternative hypothesis. And the nice thing is that if that classifier, for example, has enough capacity and you train it on enough data, then eventually the classifier that you build as at will approximate the Bayes optimal classifier, which is known to be then equal to the ratio of the likelihood of the alternative over the sum of the two likelihoods. And this is really nice because if you are doing a good job at solving this binary classification problem, you will be close to this optimal Bayes optimal classifier. And then that means now you can recover the likelihood ratio by taking 1 minus the output of your classifier over the output. And then you would recover back the likelihood ratio of the null hypothesis over the alternative. And and this is where exactly machine learning can help, because solving binary classification problem is something that now we can do pretty well using deep learning. Then you can generalize this, of course, when you will want to not only evaluate the likelihood ratio at some specific and fixed value, theta 0, theta 1, but you would like, for example, to scan over different parameter values. And then the trick is the same, except that now you would parameterize the classifier by the values, the model parameters directly, and you would give them as input to the classifier. And then you would pit the classifier against this parameterized hypothesis, against some fixed and what we call reference hypothesis. You would obtain the same optimal quantity. And then from this ratio of some now free model parameter theta 0 against a fixed reference hypothesis, that's something you would obtain by this classifier. And then you could then take the ratio of this ratio, right, in order then to evaluate the likelihood ratios at two model parameters value of your choosing. All right. And then, so now that we have this parameterized classifier, that means we have a way to basically obtain this test statistic for any values of the model parameter. And so if I have to summarize then the approach, the inference approach, I would do this. So the first step would be that you run your simulator at different values of theta, right? And then for each of them, you would produce observables X. And that constitutes your training data. And then what you do is that you train a classifier that would take as input now both the model parameters and the observables. And then you can make it such that this classifier can be used to approximate the likelihood ratio for some free model parameters theta, right? And then once you have this likelihood ratio, you can proceed and do inference. So for example, if you have collected enough data, then you can use the likelihood ratio to compute some test statistics that you know will, for example, behave like a chi-square distribution, and then go on and derive p-values for the data, or for some model parameters. All right, so what time is it? So I will maybe skip this part, but this is just to say that there are some maybe quantities in your computer program that you can use to improve sample efficiency. This is what we call gold mining. And indeed, this improves a lot. And that will not change the inference procedure. It will just augment the training data by having in some way, some additional label that comes together with theta and x, and that you can use to augment the loss. And that would result in dramatic improvement for the efficiency. But I will show that later when I go to some concrete examples. What I would like to tell you now about is how you can use basically the same kind of idea if what you are rather interested in is to obtain a Bayesian posterior. And so you could either go on and use approximate Bayesian computation, but that would be very slow and very inefficient because you have to make the same kind of choices. You would have to decide on some summary statistics, exactly as you had to do when you were building histograms yourself. And you would have to set other properties of the other hyperparameters of the algorithms, like you have to decide on the distance between the summaries, and then you have to decide on a threshold that would basically decide which of the samples that you, which of the model parameters that you samples, and then you keep. And then it would only be exact in the limit where this acceptance threshold goes to 0. And as it's closer and closer to 0, that means that algorithm, that loop is more and more inefficient because most of the model parameters would just be discarded and you would just be simulating basically for nothing. Okay, so I was telling you that you can amortize the computation of the Bayesian posterior by viewing the Bayes rule as a product of a ratio of two densities times the prior. And the ratios of these two densities is something that you can learn with machine learning, exactly in the same way as we did before. And the trick is, again, to take a classifier and to have this classifier learn to distinguish now between pairs x and theta that would be drawn jointly from the joint distribution over x and theta against pairs x and theta that would be sampled independently from their marginals. And then if you do that, what you will end up with is, again, an optimal classifier that would approximate the ratios of the joint densities over the sums of the two densities. And again, using the same trick, if you take the output of the classifier over 1 minus the output of that classifier, you would find back the ratio of the joint over the ratios of the marginals. And you would have the priors that simplifies, and then you would be left with the likelihood to evidence ratio, which is the things that we wanted to approximate. So that works. And that gives you a way basically to then amortize the computation of the posterior. And when we did that, you don't have to run then any MCMC or whatever. You have a direct access, by the way, to the once you've learned this, like here, you have a direct access, a direct way to evaluate the density of the posterior at any x and any theta that you wish, which is kind of nice. All right. And so that means also, so that gives you a direct way to sample to evaluate the density, but not to obtain samples from it. So if you want to obtain a sampler, you can invoke MCMC to do that, because in MCMC, typically what you would do is that you would run this Markov chain in order to explore the posterior density. And in between two steps, what you would do is that you would draw some candidate parameter proposal theta nu, and then you would either accept or reject this proposal by computing some function of the posterior density ratio, right? So you would evaluate the posterior density of these candidates against the posterior densities of the current value. And that, right, this ratio of two posteriors by the Bayes rule can be expressed in this way as a ratio of the likelihoods times the prior over the model evidence. This, the model evidence simplify, then we are left with a ratio of priors, and that we can evaluate. And then we have a ratio of likelihoods, and that's something we can learn again, or we can evaluate again by using, instead of the ratio of the likelihoods, the ratio of the ratios, right? And that would be equal to this ratio of likelihoods. And you can even then extend this to more efficient algorithm like Hamiltonian Monte Carlo, but then they would need access to the gradient of the likelihood function, but that's something you can do as well, because the gradient of the likelihood function is the same as the gradient of the ratio over the order ratio. And so this is nice. So that means you can use then this trick to, if I summarize, to amortize, to learn the likelihood to evidence ratios, then this allows you to evaluate directly the posterior density at any values of the model parameters and any observation value. And also to use this quantity, the ratio, inside an MCMC samplers in order to obtain samples from the posterior density. Right. So maybe I will skip that in the interest of time, but this was just to show you that there are some ways to evaluate the goodness of the posterior that you would obtain. The difficulty basically is that, and this is a central problem in approximate Bayesian inference, that you define a procedure that gives you approximation of the posterior, but then it's difficult to assess if these posterior are wrong or not, because you don't know the true posterior in practice. right? And so there are different diagnostics that you can run. There are necessary conditions, but not sufficient, unfortunately. All right, so I will just skip this and then show you a few applications on which we will apply this technique. The first one, of course, is the one I started with, so particle physics. So in this experiment, what we did was to consider an extension of the standard model, and then we were probing two parameters, two coefficients in this extended standard model, and we wanted to do inference on this. Of course, this was just on synthetic data, but this was just for the purpose of showing that you can use this method on this kind of problems. And here, what you see in the plot on the left is a comparison between the error in terms of the likelihood ratio that you would obtain using, for example, 2D histograms against one of those machine learning methods. And so in green, this is a method that would just directly try to approximate the likelihood ratio. And what you see is that eventually, as the size of the training data gets bigger and bigger, you reach an accuracy, you reach an error level which is below the one of that you would obtain with 2D histograms. And the other curves that are shown here are correspond to methods in which we use this additional data that you can get from the simulator. And the one which is the most interesting is the one in red, which is based on the extraction of the joint likelihood ratio and on the joint score, which are quantities that typically you can extract, even though you would not be able to extract the original likelihood ratio or the original score, because this would be intractable. But the joint values, which depend actually on the particular trajectory that you traverse in your computer program, is something that you can get from the simulation. And you see that we reach an error which is below the one of 2D histograms, but also when you compare that to the straightforward likelihood ratio trick in green, we gain around 2 orders of magnitude. That means we reach the same level of performance using, in this case, more or less, it's a factor 100 in terms of the training sample that you would need to generate to reach this level of performance. So that means we gain quite a lot. Then I will skip this. Another use case, which I think is nice, is so that problem is a problem from cosmology, in which what we wanted to do was to study the dark matter substructure using as observations gravitational lenses. And so, as you know, I suppose, a gravitational lens is the effect of the light bending around some very massive object, which is placed between some observer and some object which would be further away, which is the galaxy. For example, could be a galaxy. And because of this distortion, what would happen is that if you look in the sky, you could see this kind of phenomenon in which what you see at the center is the object in the middle, which could be a galaxy also, but you see some kind of ring around it. And actually, this ring corresponds to light, which is emitted by an object which is below the one in the middle, right? So this is something which is quite well known. Now, we wanted to combine that with the study of dark matter. And in particular, we considered a model that would describe the distribution of dark matter subhalos in the, for example, in the universe. And the effect would be that depending on how these dark matter subhalos would be distributed, they would have some effect actually, because they would gravitationally interact with the light, or with the yes, I think with the light, or with the thing in the middle, and they should have an effect on the actual lenses that you observe, right? So basically, what that means is that if there is if there is dark matter, and depending on how it's organized, how the clumps of dark matter are distributed, then you should expect to see things slightly differently, or that should have some consequences on these lenses that you see in the sky. And so indirectly, then that means you can use these observations to do inference on the parameters that would govern the model that you postulate for the population of this dark matter. Right. And so this is what we did. And what you see here is so on some synthetic data, but what you see is that as we condition on more and more observations, then we can do inference in this case on 2 parameters. And you see that as we condition on more and more of them, the uncertainty or the size of the posterior decreases and collapse, in this case on the nominal parameters value that we use to generate these observations. And again, this is nice because this is showing that we can use this technique, even though here the observations can be of quite high dimensions. So these are images, and the process itself can be quite complicated to describe. So again, we don't have access to the likelihood, but we can generate this data. And finally, the third example I would consider is again related to dark matter and to the fact that if there is some dark matter clumps in the universe, then and if we postulate that the dark matter exists as a particle, then the mass of this particle should have an effect on the distribution of the population of these clumps, right? And depending on this value, then they should have an effect also on other objects. And one of them is stellar streams that we observed in galaxies. So what you see here in the background is the Milky Way. And then around the Milky Way, we have found 2 stellar streams. The first one, which is called GD1, and the second one, which is called Palomar 5. And what is interesting to observe is that, for example, in GD1, if you look at the densities of stars in this stream, then we find a gap at some position, at some location around here. And one explanation for this gap would be that it is the result of an impact of a dark matter surveillance, or clumps of dark matter. And so this is, for example, simulated data in which you see a stream above which is not perturbed by a subhalo, and then below which would be perturbed by 2 subhalos. And you see basically that these subhalos basically kick out some of the matter out of the streams, right? And so again, that means now given some, if we could simulate that and simulate the effect of this matter being kicked out of the densities, then that would give us an indirect way also to do inference on the mass of the dark matter particle. And so this is what he did in the study. And we applied exactly this methodology. The data, the observations here were described as some kind of densities. So the stellar densities on the stream. And then we just train exactly this kind of likelihood to evidence ratio as a neural network, which we combine with the prior on the model parameters on the mass of the dark matter particle to then obtain a posterior. And so I picked also this example because on this one, we computed these different diagnostics that I skipped, unfortunately, but which shows that the approximation of the posterior appear to be correct, even though we have no certainty about that, but at least they pass our 3 diagnostics that we consider here. All right, and then at least for the simulator that we consider, but which was, in our opinion, a bit too simplistic, is suggests that when you do inference on the GD1 stellar stream, it would suggest a strong preference over for CDM, so cold dark matter, over warm dark matter, meaning basically that the range of values for the mass of the dark matter particle should be above, in this case, I would say 10 or more. So that means you can use that then to exclude theories in which the mass would be in this range from, for example, 0 to 10. All right. So finally, so I will now look a bit further away and tell you more against about the frontier, so the family of methods that you can use to do likelihood tree inference. So today I've told you about histograms, approximate Bayesian computations, neural likelihood ratios, summary statistics in a sense, because you can view likelihood ratios as some optimal summary statistics. And then I skipped the gold mining part, but I showed you one example where this is applied successfully. And so, as I said, there are other techniques, and this is beginning to be an active field of research. You see more and more papers at machine learning conferences about this topic. Instead, what we could have done was to try to directly approximate the likelihood function, and then with this piece move on and do, for example, MCMC with this approximate likelihood ratio to likelihood function to approximate the posterior. Or we could have directly tried to obtain the posterior itself, and that's something you can do as well. And as you make progress on the machine learning front, you will be able to improve. You will be able to tackle data that are of higher and higher dimension. And so this is something that progress in machine learning will directly enable. That will allow to consider problems that are further away on the spectrum. However, this will not solve the problem, which is due to the fact that running the simulator is maybe quite expensive. It may take, I don't know, maybe minutes just to generate an observation. And in this case, your computational budget may not allow you to generate millions of samples that would be necessary in order to train these machine learning models. So in this case, you need to be a bit smarter. And so there are different approaches, and many of them are just sequential variants of these ones, in which you would try to approximate this quantity, this likelihood, this ratio of the posterior in some kind of rounds. And at every round, you simulate a few observations, and then you would use them to improve your approximations, and then you would proceed like this iteratively until you converge. And that's something which has been done as well. And this is reminiscent to what is also done in more generally in what we call active learning. And then finally, and this is this would allow you then to consider simulators that are more expensive. And finally, the third direction that we identify, which is what you could be enabled by the tighter integration of the computer programs with the inference code. And so by that, we mean techniques that would be inspired or derived from, for example, differentiable programming or probabilistic programming that will allow you to extract this additional information from your computer program and not to see it anymore as a black box. And so that means I think in the next years or so, we'll see improvements coming from these three different directions that will enable simulation-based inference to be applied to more and more challenging problems. So we summarized this in a review paper that we wrote last year with Kyle and Johan, which is the topic of today's talk, the frontier of simulation-based inference. We also summarized different families of algorithms, and we discussed these three research directions. So to summarize with today's talk, I would say that, and I will conclude by saying that much of modern science is based on simulator, and that you can use to make precise predictions in a way which is very natural. But at the same time, this same formalism is making inference quite challenging. However, machine learning enables powerful inference methods, and they can work in problems from the smallest scales, from the smallest to the largest scales, as I've shown in the examples that I've picked. And I think further advances from the machine learning community will translate in direct improvement to this method. And that means for the scientists, it will also enable them to ask new questions and hopefully to lead to scientific progress in general. All right, and finally, let me thank some of my co-authors that were directly involved with the work I presented today. So Carl, Juan, Johan, Yuri, Siddharth, Christophe, Neil, and Gianfranco. And if you want to read more about that, we have a few references that are shown here in this last slide. And that's it for today.
Thank you so much. Over time, of course, kind of due to the interruptions, but if you are able to stay, I think we can have time for questions.
Yeah, sure, yeah.
Oh, right, people. I think we can unmute you if you like have a question, if you raise your hand or something.
I think people can unmute themselves now.
Okay.
I just changed the setting, so try it. If not, raise your hand.
Yeah. Sorry. Yes, David also here. Sorry, I don't know how to raise my hand, so I unmute myself directly. Thanks to Gilles. That's the first time, of course, and every time it's clearer and clearer. I do have questions. Whether okay, maybe you don't have time in this kind of seminar, but is there any tricks in terms of activation function, batch normalization, dropout, whatever, which are specifically advised to be used for these techniques?
But it depends. If for the likelihood ratios, I would say yes, there are a few tricks that we have learned to be important. They are described in the papers, but and they are not necessarily always well implemented in some packages that try to implement these techniques. So, for example, one thing that we've realized that was really important is when you build this, this batch of data from one or the other hypothesis, what we found to be quite important is that it's probably better to not draw actually different X values. What you could do is to draw ones from the joint, and that would give you the first half of the mini batch. And then instead of populating the second half with samples that would be drawn directly from this product of marginal, you can reuse the first half, but then simply shuffle the theta values. And that will result in a batch which would effectively be equivalently, which you can say would have been sampled from this product of marginal, but by doing so, you're also reusing the same X values. And so that will force really then the classifier to focus on what's making these two distributions different, because what could happen is that they just find, they see other X values that are quite different from the X values in the first half, because the data is so largely, is so high dimensional that would be very likely to happen. While what we want is for the classifier to focus on really what is basically connecting or linking the X and the theta values. So that's one trick that we use, and that often leads to better results. Then regarding the architecture themselves, that depends, of course, on the data, on the nature of the X data. What is not clear and that would need more work is how do you then, because this classifier should take as input both the data and the parameters. And so it's not always very natural to mix directly these two quantities in a first layer of a neural network. What you would usually need to do is to architecture the network with two different networks, one which would ingest the data only and would be some kind of embedding. And then later on, this embedding is concatenated with the parameter values and then fed into some upper part of the network. But there are many other ways that you could do using hypernetworks or conditional convolutions or these kind of things. That's things we've explored a bit, but that would need more work to give you strong guidelines to follow.
Thanks a lot.
All right.
I guess, can I ask one more question?
Yes.
So you showed, it was early on, maybe like slide 10 or 11, the projection for that Higgs discovery onto L4, whatever axis. Why would you want to do a projection onto a lower dimension in this case versus trying to perform some analysis in, all four momentum space, or, a non-projected space?
Because, I mean, to do that, you would need to fill in histograms. And even with few dimensions, you would be cursed by the curse of dimensionality. So the number of samples you would need to generate to fill sufficiently each one of the bins, and even with 3 or 4 or 5 dimensions, because the number of samples that you would need to generate would scale exponentially with the dimension of the data that you are considering, right? And so I don't know how many, what would be the dimension in this case, but I suppose it would not be 1. And that's why then it would be practically quite difficult to then obtain a good estimate of the density of the data in this space. And that's why you would need to reduce it into a space of smaller dimensionality, for example, in this case, just the real line, because then it's much easier to fill the bins.
Right. Okay. Yeah, that makes sense. Thanks.
Thanks. Any other questions? Okay. Thank you so much again. And we'll post the edited video on YouTube.
Yes.
Yeah. All right. Thanks, everyone.
Thank you.
Bye.
Thank
Bye-bye.
you. Bye.
Thank you. Bye-bye.